Hello, my name is Isaac Smith, and this is a video course on quantum mechanics. This video I just wanted to outline what I'm hoping to do in this course, hopefully if everything goes right. And so I start off here on quantum mechanics. In my quick definition of it is the physics of small things. And you've probably heard of it relating to atoms, or maybe even things smaller than that, like electrons or neutrinos, right? And this is the physics, the laws of the universe that those things abide by. And just a little disclaimer here, it's not just small things. There's not a certain level of size that you stop obeying quantum mechanics. It's just that the effects of quantum mechanics are so small that they're only noticeable with equally small things. Everything in this universe obeys quantum mechanics, or as far as we can ignore relativity and certain exceptions that are still being researched to this day. But in like the classical world, everything obeys quantum mechanics. It's just that the results of quantum mechanics, the changes to classical physics and quantum mechanics brings, are so small that with in our macroscopic world, we cannot detect them at all. So the topics of study, again, hopefully these will be the topics covered. I'm going to start off with the beginnings of the quantum theory, and that's going to cover things like basic experimental results, the existence of quantum spectra, or quantized spectra of hot gases, as well as the photoelectric effect, the double slit experiment, an interpretation of that, the wave-particle duality, the Stern-Gerlach experiment. I'll talk about the Bohr model, which was the early 1915 basic quantum mechanical model. It is not correct, but we will discuss it and see that it actually has some bearing in modern quantum physics. As well as at the end of this, I'll go with some things that quantum mechanics will eventually give us, such as the periodic table and electron configurations, where we'll eventually be getting here and show by the end of 7 here, we'll be able to show everything that we sort of see in our periodic table, which has profound uses and applications in chemistry. And you've probably heard of some of this if you've taken a high school chemistry course. So then we'll talk about Hilbert spaces, which is the type of mathematical space that quantum mechanics takes place in. And if that doesn't make sense to you, hopefully it will soon. Then we'll talk about a variation of a Hilbert space, a function space, which will set the stage to talk about the Schrödinger equation, the big central equation, you might say, of non-relativistic quantum mechanics. And we'll be solving that and talking about its solutions. That's going to be a really big topic here. Then we'll talk about matrix mechanics, which is an alternative formulation. It came before the Schrödinger equation. And it is a different formulation of quantum mechanics. Both wave mechanics, which is the Schrödinger equation, and matrix mechanics are incredibly useful to understanding the whole quantum theory. So we're going to, of course, have to study both. And you really need both to get a full picture of everything quantum mechanics can do, which we're not, of course, going to get to everything. But the groundworks of it still require you to understand both wave mechanics and matrix mechanics. Then everything here, 1 through 5, is going to be pretty much exclusively in one dimension. And in quantum mechanics, one dimension, even though we live in a three-dimensional world, one dimension, it tells us an incredible amount of what we can expect to see in 3 dimensions. We'll just, number 6, we'll generalize everything we've done in 1 dimension to 3 dimensions. It's not actually that hard. Once you understand 1 dimension, 3 dimensions is pretty easy. It's similar topics, just a little bit of different mathematics. Number 7, we will go and talk about spin and its applications. And that spin has a really profound impact on quantum physics, as you will see. When I'm talking about its applications, we will talk about, and we'll set the groundwork for the theory of spin. We'll talk about electrons and magnetic fields. We'll describe more about the Stern-Gerlach experiment that I mentioned in the beginning, and that I'll have a video on. We'll talk about the mechanics of how that works. We'll talk about a lot about angular momentum and how that sort of creates the periodic table as well. We'll talk about the spin quantum number, which is very important for the periodic table. We'll talk about the Pauli exclusion principle, which one could say builds the periodic table. It's really the only reason it's a table. And we'll talk about that in relation to spin. We'll talk about the spin statistics theorem, not proving it, but it's a very important and impactful theorem that can be proved with relativity and quantum mechanics. We'll talk about exchange forces, which goes along with the Pauli exclusion principle and the spin statistics theorem. And then we'll talk a little bit about solids, which are very interesting. The quantum mechanical theory of solids is one of the most interesting things in modern physics that, on an introductory level. It is very interesting, and it combines a lot of the quantum mechanics that we do. Finally, we'll talk about some further explorations in quantum mechanics. That's going to cover some introductions, right? Not really delving into topics very deeply, but introductions to other things in quantum mechanics. We'll talk about a new technology that is getting developed, quantum computing. We'll understand that. We'll talk about that in relationship to entanglement. And we'll talk about one of the great debates in physics history involving Albert Einstein and how he sort of tried to argue the quantum theory is incomplete. And we'll talk about his paradox called the EPR paradox. It really isn't a paradox, and we'll talk about that, and it's very interesting, the history of it. Finally, we'll talk a little bit about perturbation theory, which allows us to solve far more complicated situations. We'll solve for the dynamics, the quantum mechanics of very complicated situations, or at least more complicated than what we'll be able to do with just solving the Schrödinger equation simply. And then finally, we'll talk about quantum field theory, which is our combination of relativity and quantum mechanics. And of course, we'll talk a little bit about relativity in that as well, as much as it pertains. So in this course, the features of this course will include some many videos on introductory topics in quantum mechanics. I'll also have videos on prerequisite material, such as topics in math and elementary physics, and I'll label those with 0.1, 0.2, etc. This video is just an introduction video. I'm labeling it 0.0. And then I will have notes and or references and problems in the description of every video, including this video. I'll have some resources just for quantum mechanics in general, some nice textbooks, and also some references for the prior knowledge that is recommended. Of course, though, I cannot cover all the prerequisite material. I'm going to assume you have some knowledge. This is not all necessarily required, and I'll explain that in a minute. But I do strongly recommend you have a strong understanding of mathematical physics through an honors physics level in high school or equivalent. Not every school has an honors physics class, but an introductory college level physics class, AP Physics 1 or 2, would be sufficient. If you have AP Physics C or a calculus-based physics class, that is definitely enough and would mean you would understand most of the material here. Some of the prerequisite videos I'll make will not be necessarily this knowledge, it will be a little above it. So just because you know all of this doesn't mean you can necessarily skip this and understand everything. Finally, mathematics through a Calculus 1 course, as well as a solid understanding of algebra, vectors, and trigonometry. Algebra, vectors, and trigonometry is going to be pretty much required. I'll have some videos on it, but it's going to be very surface, and review oriented, not really what you would need to know for this, just making sure you get the basics of it. So a solid understanding would be very important. If you don't have calculus, it's not really the end of the world for this course. If most quantum mechanics courses require you to have knowledge up through a calculus 4 or differential equations course, sometimes even with linear algebra. And I'm trying to minimize that in this course. Of course, there will be, Calc 2, Calc 3, Calc 4 topics that you'll need to know, but I'll be walking you through those. And you really can't get through quantum mechanics at all, not even remotely, without being able to solve a differential equation. The Schrödinger equation, the central equation, is a differential equation. Sometimes you'll need some Calc 4 strategies to solve it. And so I'm not going to skip those, but I'm going to walk you through them. And the reason I'm doing this is, quantum mechanics is generally very restrictive as to who can learn it. You have to know differential equations, you have to know multivariable calculus, a lot of the times you have to know linear algebra. And quantum mechanics textbooks assume this all as prior knowledge. So I'm trying to get a quantum mechanics course out there that has far less required prior knowledge, and be more user-friendly in explaining things, so that even if you don't have all of the math that most textbooks would require for a quantum mechanics course, you can still learn it, because quantum mechanics is an extremely beautiful, it's an incredible theory. And so I kind of want to get that available to more people, not just people that understand differential equations and understand linear algebra. So, and so some of the more advanced topics, you don't have all that math, you may not understand. But the great thing is you can see that there is, a derivation for the results that you'll see. The results will be more simple. The mathematics that derives it will be more complicated. And if you don't understand all that mathematics, that's really fine. You can see that there is a derivation. You can trust that, I'm giving you a good result. But also, understanding that there is a way to get to the result is just as important as understanding the result. So I want both of those to be taught in this course. So if you don't have all of this, you don't have to shy away from this. As I said, quantum mechanics is extremely, extremely beautiful, and I don't want this to stop you from learning it. Just if you do learn it, you don't have all of this, you may not understand everything, but you will hopefully get an appreciation for it. And if there's, math that I don't cover very well, I will have I'll have references in the description for both, for other videos, for texts. I'll have notes as well. So I really just want this to be a fun and intelligent course that you can learn from and understand the beauty of the quantum theory. So I will see you in the next video.